Why are quantum circuit measurement results probabilistic? Imagine flipping a coin that can land on heads or tails, but before you look, it's actually in a mix of both. That's similar to what happens when we measure a quantum bit or qubit. Instead of being in one clear state, it exists in a superposition of multiple states at once. When we perform a measurement, this superposition collapses into one definite outcome, either 0 or 1. The chance of each outcome depends on the qubit's quantum state before measurement. A qubit state is described by a wavefunction or a quantum state vector. This vector contains complex numbers called probability amplitudes for each possible outcome. The probability of measuring a specific result is calculated by taking the squared magnitude of its amplitude. For example, if a qubit is equally in a superposition of 0 and 1, measuring it will give 0 half the time and 1 half the time. This is called the Born rule, and it's fundamental to quantum mechanics. This probabilistic result isn't because of any lack of knowledge or mistakes in the experiment. It's built into how quantum physics works. When you measure a qubit, the process is inherently unpredictable and irreversible. It turns quantum information into classical information, and once measured, the qubit is left in the state you observed. It can't go back to its superposition form. In quantum circuits, measurements are often modeled as projective measurements. This means the quantum state is projected onto one of the possible outcomes, and the probability of each is given by the trace of the product of the measurement operator and the quantum state. If you don't record the measurement result, the state becomes a mix of all possible outcomes, weighted by their probabilities. When building quantum algorithms, this randomness means you need to run the same circuit many times, called shots, to gather enough data to understand the likelihood of different results. This is essential for tasks like quantum error correction, quantum cryptography, and quantum simulation. Sometimes, measurements are done during the computation itself, called mid-circuit measurements, which can help adapt the circuit based on earlier results. But no matter how you do it, the outcome remains probabilistic because of the superposition principle. In summary, quantum measurement results are probabilistic because qubits exist in superpositions with complex probability amplitudes. When you measure, the superposition collapses into a definite state, with the chance of each outcome dictated by the amplitudes. This core feature of quantum mechanics sets quantum computing apart from classical computing and influences how we design and interpret quantum circuits.